Today we're going to talk about how equilibriums can shift if we change our conditions, and this is called Lechatellier's principle. Lechatellier's principle tells us that when a stress, which is just a change in condition, is placed on a reaction at equilibrium, the equilibrium will shift in the direction that relieves the stress. Okay, and so we're going to talk about how this works with different kinds of changes that could happen, and usually we're going to refer to whether the stress that we add to the system will favor products or will favor reactants. And I will frequently say that we'll either shift left or shift right. So the products are on the right, so a change that favors products will be a shift to the right, and a change that favors the reactants would be a shift to the left. All right, so we're going to go through a couple of examples, and I'll use that terminology, so I just wanted you to understand where it comes from. All right, so if we add a reactant, so let's say that we have a system at equilibrium. We're going to use our little balance here as an indicator, okay? So at this point, the concentration of products and reactants are not changing. Okay, but what if we add a reactant? So we're going to add some more to this side, all right? That's going to make our little balance here off balance, and it's going to mean that there's more reactants than there should be. So in order to relieve that stress, reactants will need to be converted into products, okay? So if we add a reactant, we favor products, and that will be a shift to the right, all right? Now, if we remove a reactant, that is going to be the opposite, right? So instead of adding something here, we're going to take something away, all right? Which means that now we have too many products for our equilibrium because there's not enough reactants there anymore. And so this change would be the opposite, as you would expect, and it will be a shift to the left, okay? If we add product, so now we're not here. So if we add product, that's shifting it this way. So now we have too much on the right side of the reaction. And so in order to compensate for that, the reaction will again have to shift left. All right, and then now for the last one, if we remove product, that's just the opposite of what we just did, and we'll have to form more products in order to reestablish equilibrium. Okay, so that's how changing the concentration affects our equilibrium. All right, the next next stress we could add to the system would be if we add a catalyst. All right, and a catalyst, this is one students often get confused, but a catalyst will change the rate of the reaction, but it has no effect on the equilibrium. So all that means is that your system will get to equilibrium faster, but the amount of product and reactant that are present doesn't change. In terms of gases, the volume is going to make a difference in terms of what our equilibrium is. So if we change the volume, we change the concentration of a gas, because remember, a gas will take up as much space as it's given. And so we need to look at how that volume change is going to change on both sides of our equation, and the side that's going to be affected most will determine which direction our equilibrium is going to shift. So I'm going to do a few examples of this because it takes a little bit of getting used to. So in the first case here, we have two gas molecules here, one here, so that's 3 total on this side, and we have 2 over here, so that's 2 total on that side. Okay, so if we increase the volume, then our concentrations are going to go down. So the concentration of these gases will go down, and the concentration of these gases will also go down. Okay, but we only have 2 molecules of gas on this side, and we have 3 molecules on this side. So the change is going to be even bigger here. So if we'll draw an arrow for each molecule that's going to change, then we have 2 molecules on one side and 3 on the other. And so the effect is going to be biggest in the reactants. So if our volume goes up, our concentrations go down, and that effect will be larger in the reactants. So we have less reactants than we do products, or a bigger decrease in reactants than products. So we need to make more reactants in order to compensate for that change. So that will be a shift to the reactants or to the left. Right? If the volume goes down, then we've concentrated everything, and that concentration will be more on the reactant side because there are more molecules of gas there. And so in that case, we will favor products, and it would be the opposite direction. All right, so in the next one, we have a molecule of H2, a molecule of I2, so that's 2 over here, and we have 2 HIs over here, so that's 2 over here. All right, so in this case, a change in the volume is going to have the same effect on both sides. And so the result will be that whether the volume goes up or the volume goes down, the change is going to be the same on both sides, and so you won't actually see any difference if you change the volume. So if the molecules of gas on either side are the same, then neither of these will have any effect. All right, so in the last case here, we have 2 molecules of gas over here, and we have 2 plus 1, 3 over here. So this is going to be the opposite of our first one. So if the volume goes up, our concentrations are going to go down. So that's 2 down here and 3 down here. All right, and so our concentration is going to go down more on the product side, and so we will favor products or a shift to the right. And if our volume goes down, then our concentrations will go up on both sides, and that concentration change will be greatest in the products, and so as a result, we'll have to convert some of those products back to reactants to reestablish equilibrium. The last stress that we're going to talk about is a change in temperature. So we learned earlier this year that an endothermic reaction is one that requires heat, and so we will frequently write heat, or one way to represent that is by writing heat as a reactant. And an exothermic reaction is one that produces heat, and so heat is sometimes written as a product. So there are much more complicated explanations for this based on thermodynamics, but for the sake of what we're doing here, we're just going to treat heat as a reactant in an endothermic reaction or a product in an exothermic reaction. And so if we do that, then we can just treat it like a change in concentration of products or reactants like we have in our previous problems. So if you were to increase the temperature for an endothermic reaction, so if T goes up for an endothermic reaction, then that's going to be like adding reactant. So we need to get rid of that heat, and so that will shift the equilibrium to the right. Okay? If for an endothermic reaction we decrease the temperature, that's like removing a reactant, and so we would make more reactant to compensate for that. Okay, for an exothermic reaction, it's going to be the opposite. So if our temperature goes up, that's like adding heat, which is already a product, and so we'll need to make reactant in order to compensate for that. And if our temperature goes down, that's like removing product, so that's going to shift our equilibrium to the right to make more product to make up for the fact that we've removed one. Okay, so like I said, there are more detailed thermodynamic explanations for this. If you take AP, we'll go into it a little bit more, but for the sake of this class, we're just going to use this as our method of determining which direction equilibrium is going to shift if we have an endothermic reaction or an exothermic reaction. So it's important to notice that the temperature change doesn't always shift the reaction in one direction or the other. You have to know if it's endothermic or exothermic to know how a temperature change is going to affect it. All right, so we'll do a few examples with this, and we're going to look at a equilibrium reaction in the lab next week and look at how we can use Lechatelier's principle to predict which direction that equilibrium is going to shift.